How's everybody doing? You're doing all right. I thought you might be like asleep by now, but you're not asleep. This is good and slightly scary, so excellent. Good way to start. Somebody gave me a note yesterday and asked me a question that I thought was really, really well worded. And I wanted to start off, I changed my talk a little bit last night because of this, and I wanted to start off revisiting a slide that you saw a very long time ago, which was yesterday. It's the dark side slide. And it was a question regarding if there is a place for basic research and theoretical physics in doing good in the world, essentially. And the answer to that is absolutely yes. I've been focusing a lot on applied research, and I will talk about applied research today because that's what I do, and that's my happy place. That is not necessarily other people's happy place. So your goal is to find where your happy place is here so that you can do amazing work, so that you can fulfill your passions, and you can make the world a better place. So you have to figure out where you are on that line. There's good and bad in all of it. And I was thinking a little bit, you know, these things might seem obvious, but they get more and more blurry as you sort of go on to your career. What does it mean to do good work, and what does it mean to do bad work? You can do really bad theoretical physics, and you can do really good, incredibly applied engineering. It really depends on how you do the work, the integrity of your work, how you treat other people. And so, you know, I think sometimes Vader gets a little bit of a bad rap. You know, some of this is, you know, are you a Slytherin or a Gryffindor or whatever? I mean, you know, whatever your personal house is. Yeah, there's going to be a lot of Ravenclaws here. I know. I underwent a very painful transition from Gryffindor to Slytherin, so we'll talk about that another time. But it's really about figuring out what you're passionate about and what you're good at. You know, and there's a lot of room for this. And bless you, theoretical physics people, because that's not the easiest life in the world. You better like to teach, or maybe you could work at a national lab or do some sort of government-funded research. But it's definitely maybe a harder path, so you really have to have passion for it. But it's amazing, and thank you for what you're doing. So whether you want to see an impact from what you do in 3 years or 300 years, which is very generous of you because you won't be around to see it, the work that you do is going to be important, okay? And it really just depends on where you fit, where your personality fits, where your passion fits, in terms of where you should be on that continuum. So today I'm going to talk about some more really quite applied work, how to make decisions in this space, which goes for working in government at ARPA-E or being a venture capitalist or doing something in industry. We all think about a lot of these things in the same way. So it's going to be really applied, and sometimes it's going to be a little like business speaky, which is something you learn to get a tolerance for. But at the end of the day, it all relies on doing really good technical work with integrity. So I want to make sure that that's understood. So let's move on to the talk. You will notice that I have not put the ARPA-E logo on anything, and I drew about 40 rectangles and filled them in white to block logos because, thank you, PowerPoint, for the way you do slides. Because it's really important that, again, I'm here just on my own. I'm taking vacation to be here. I'm not representing the agency formally, and that's actually really important. It is a government agency. I am a federal employee. I had to get permission to be able to come here and do this and make sure that the government wasn't actually paying for my travel and stuff like that. So these are just my own thoughts, but I am going to talk about the agency and how it works, how we use money, and how we make decisions. And that's okay. And these slides I'm showing you are all public. They're all available at different parts on different websites, things like that. So I'm not telling you anything that it's not okay to tell you. So what is ARPA-E? We actually have a mission that is actually written in law. We have money from Congress, and our goal is economic, energy security, and being a leader in terms of advanced technology. We're a very young agency. We really started about 9 years ago. It was actually under President Bush at the time with this thing called the American Competes Act, and we've grown every year. And it's pretty crazy when you think of this starting it. There was nothing, and then all of a sudden, there were millions and millions of dollars. And you have to figure out how to put together programs and funding announcements and actually give the money and manage the money. And it's really crazy for a few years in terms of an agency getting started. In government, a lot of times agencies have been around for a long time, and there's procedures for the procedures, and then there's acronyms for the procedures and acronyms for the other groups of acronyms. And here this is young, crazy agency trying to do this super high-risk research that nobody else would touch. There's a role for us, and it's to sponsor that research that nobody else will touch. So we work on problems that are of interest to the country as a whole, the rest of the Department of Energy, and the world. But the area that we focus is this sort of a little bit crazy, high-risk stuff that nobody else will touch. If it works, will it matter? Just because we're doing crazy research doesn't mean that we can ignore what it needs to look like if it's going to be successful. And so this is the part that sort of gets into that applied area. If you're going to make a fusion reactor work, what does that have to look like for it to make an impact? If it works, will it matter is sort of one of our foundational sayings that we think about all the time. And we sort of emphasize over and over that we're not working on incremental technology. We might not be finding the entire solution to something. For example, we have a program in fusion. It's not to solve fusion. Fusion is a huge thing, and I think you saw some talks on it. But it's a program around building tools to enable much, much faster development and cycles of learning in fusion, which is incredibly important. So in that case, there can be a huge impact to that tool being successful, and that's what that program is about, for example. And here's what our portfolio looks like. There are programs here all across the board. Let me see if I can. This is important. Gosh, these screens are so huge, you can hardly see that. Here's Alpha, which is that fusion program I was talking about. We do have some programs in solar, but it's very interesting ways of trying to use very, very high efficiency materials in a way such that it's actually makes sense from a cost perspective. We have programs trying to understand how we can get more renewable penetration into the grid. This is something that Australia really cares about and faces issues with, and I think has done a really lot of good work in this area. Every country has different challenges regarding their grid. The United States has some particularly interesting challenges, so that's a program in that area. There's a program here called Delta, which I'll talk a little bit more at the end, which I actually own and manage, that a different program director started, which is all about basically locally heating and cooling a person instead of a whole room. You end up saving a lot of energy doing that. And by the way, everybody who works at ARPA-E is there temporarily. We're all there from 3 to 5 years, and then we move on. This means that we often inherit each other's programs. This means that you self-select for people that have a healthy appetite for risk, because it means you will be finding another job in not that long. And it keeps new ideas coming into the agency. And it's one of the reasons why our agency is, I think, very strong. It's very lean. We do a huge amount with a relatively small number of people, and it works very well doing that. But it does mean that we have to help each other out with programs when we leave. We have programs that look at how much carbon sequestration you can get in the roots of plants and how you can increase that as a way to handle carbon. So we have things from agriculture all the way to something like Enlightened, which is a program that looks at data centers and how you can make them more efficient so that you have less energy waste. And that looks at things like optical interconnects and how much energy does it take to actually watch a cat video. And actually, when you see how much energy it takes for all of this information to be continuously cycled, it's a lot. So how can you make that more efficient? So it's all over the place, and that's what I'm trying to emphasize, is that we don't actually say, okay, I want to program in this now. The program directors are the ones, like me, who drive what we're going to be working on. In the life cycle of a program, your interview is actually a program pitch, which is freaking terrifying. Because with just your own extra time and freely available information, you have to put together a program pitch to say, here's what I would spend $30 million on and why. And that's really hard to do when you, A, are working another job at the same time, B, have limited resources. If you don't have access to journals, That's a real pain in the butt. But that's our interview process. Some of us continue our ideas on, some of us choose new ideas once we enter the agency. And we work for about a year actually putting this concept together, and we talk to everybody. We talk to people on the technical side for solutions. We talk to potential customers. We talk to potential fabricators all along sort of this value chain to really understand what the solution needs to look like and what the challenges are in getting there. We then put together something called a funding announcement. We go through 2 stages. People put in these short concept papers. We have encourage or discourage them, and then there's a full application process. We have external and internal reviews, and we go through this twice. It's a really huge process that's sort of defined legally. And then once we go through the selection, we put together these cooperative agreements, which means things can be changed or canceled at any time. It is not a grant, and it is a very heavily managed type of funding, which means we are there every quarter going over the data with these groups, seeing if they met their milestones, seeing if they're doing the work in the right way, seeing if we can help them, if they're getting stuck, if they need to pivot to a different path. Whenever you're doing high-risk research, a bunch of it's going to fail. It will fail. It's not going to work. You can fail right or you can fail wrong. And if you fail right, it means you know why it didn't work, you publish why it didn't work, you add knowledge to the knowledge base of the world so somebody else doesn't waste their time trying to do the same thing, and you learn from it. So I'm very happy when something fails right, because it means we've added knowledge, and that's perfectly fine. And we would expect to have quite a bit of that when we're looking at high-risk research. Failing wrong means you do the opposite of that, and maybe you still keep trying to go even though you shouldn't, or you don't publish, or you don't support that information getting out. This is a very tricky thing when you're in industry, because in industry, it's very hard to justify spending time to write work up that didn't work out. That's a tough one. But here, we are funding these people, and we can ask them to do that. So this is good. So that means that we're trying to get all that information out there. It also means we're on planes all the time. We have a team of people that we work with, and we visit folks, and we're face-to-face all the time. So it's a really exciting job because there's a lot of different technologies that we work with, a lot of different people that we work with, and so that's very exciting. It's a little tiring, but it's exciting. And how do we measure success? Well, we're a young agency doing this high-risk, crazy research, so a lot of it's not going to pan out yet. But we can look at things like follow-on funding. So we have spent about $1.5 billion at ARPA-E. Our teams have received more than that in follow-on funding to date. So that means that the private sector has valued this work and put more money into it than we have. That's a good indicator of early success. Programs have moved on to other government agencies for follow-on funding. New companies have been formed. Over 50 new companies have been formed. And actually, I think that number is even quite a bit higher now. So that's really exciting. Those are ways that you can see that programs are moving on. We look at things like number of patents, number of papers. There's a lot of different metrics for success depending on what you're looking at. So this is really important to us, and it's important that we communicate this to folks in our country because we are a taxpayer-funded organization, and it is up to us to let people know what we're doing and how successful it is. So this is not an ARPA-E slide. This is a very businessy slide, but I actually like this, and it's something that I first learned actually when I was at Dow Corning doing this new business development stuff. So how can you be successful? How can you make an impact in the world? So there's 3 things: feasibility, viability, and desirability. Feasibility is whether or not your technology works. That's the stuff in the lab. That's getting your chemistry to work out the right way. That's getting your electrical engineering to work out the right way. You want something to do something. Does it do it? That's that part. That's only one of the circles. There's another circle, viability, which is, can you make money doing this? That's really important because for most of the technology that's in the world, it has to be supported somehow by a company who's going to make it and sell it. So that part is where, say, the cost calculations come in, things like that. And that bottom one, desirability, that's marketing. That's hard. Will people buy whatever it is that you're making, and will they use it in such a way to make an impact the way you want there to be? And humans are messy, and humans are complicated, and humans often don't do the right thing. And it is very frustrating when you spend a lot of time getting something to work from a technical point of view. You can even make money making it and selling it, and then nobody wants to buy it. Or they buy it and they don't use it right, and then everybody hates it, and then nobody buys it again. That's a difficult part, and you have to have all three of those things work. That's a hard thing to do. So when we're at a place like ARPA-E and we're putting together a program, even though it's very difficult and high-risk research, we think about things like metrics. And if you meet these metrics, it means you were successful. And we put these metrics in these funding announcements. So you have technical metrics, which are challenging, but sometimes those are the easiest things to do. Cost metrics, which might be based on the amount of energy you save at a certain energy cost, for example. Sometimes those can be tricky, depending on what you're putting together. And then customer requirements. So what does the solution have to look like? What are the limitations? Who is the customer? Sometimes the customer is not the person who's actually going to be making it or buying it. That can get really tricky. So you have to understand who is going to be using your technology and how they're going to be using it. And I'm going to show you an example of a program that has a lot of metrics that are driven by that circle. So again, a lot of messy, non-technical stuff. You need all these things to be successful. And one of the reasons why ARPA-E is good at this is because we do the high-risk research. We can take completely new paths in technology that are very difficult for industry to justify, often because it is high risk, it is very different than what people are already doing. You need the freedom to be able to do that. You need the freedom to be able to fail at it. And at least in the US, a lot of industries are not willing to do that sort of high-risk research anymore. They did used to, but that's really changed. All right. So what should we work on? Remember this $30 million part? Remember the money, the good stuff? So what are we going to do? Well, here is a diagram that every single person at ARPA-E shows all the time. This is called the Sankey diagram. And this shows for the US where energy goes. They can get very complex. I actually have funded somebody who we'll talk a little bit about later to actually put together modeling and data visualization for this, but this is the most simple one. So here's all of our sources of energy. And you can see that, first of all, almost 2/3 of it is wasted. We have a lot of really inefficient systems. So about 1/3 of it goes to something useful. And so you can look at things like energy you use in a house, energy you use at work, energy you use in the industrial sector, so that would be things like making chemicals and stuff like that, and what you use for transportation. So that are sort of the 4 buckets, okay? So if you look at, this is all of the energy the US uses for everything. 14% of it is used to heat, cool, and ventilate buildings. Out of all of it for everything. That is ludicrous. That is ludicrous. It is a huge amount of energy. And when you look at what people are trying to do to make a car a little bit more efficient or make, a certain manufacturing process a little more efficient, we're sitting there just wasting tons of energy because people leave their thermostat set to room temperature all day in the winter and stuff like that. It's crazy, and it's really a problem. So when I looked at this, I thought, well, okay, that's got to be fixed. This is ridiculous. So we can make a big impact even if we can make a small change in the amount of energy we use in buildings for heating, cooling, and ventilating them. It's not even plug loads or lighting or stuff like that. It's just the HVAC. So this is sort of some of the reasons why I was thinking about this problem. And just to let you know, the reason why I went to ARPA-E is I got called by somebody who was a program director. His name was Howard Brantz. He was in the solar field. And I worked with him a little bit when I was in graduate school. He remembered me and asked me to review some proposals and stuff for ARPA-E, which I did, which took a fair amount of time. And then when he was thinking of who would be the next program director, he thought of me and gave me a call. And the timing was perfect. So there's a lesson there, which is if somebody asks for your help reviewing stuff, or reviewing journal articles or proposals and stuff like that, this will start to happen to you. Do it. because you never know when that's going to come back and be a good thing for you. So it came back and was a very good thing for me. So we keep focusing also on ways to make more energy when we could just use even just a little bit less of it. So how can we do that? Well, when we're thinking about heating or cooling and ventilating spaces, we're talking about how people feel. Are people comfortable? Are people safe? We have to think about the technology that we can use in that context. So you don't own houses yet. Okay, well, most of you probably don't own houses yet. I don't know. I'm not going to make any assumptions here. But what happens when you're not at home? Not in your dorm, not wherever. You're not in your apartment. All right? Your cat might be licking your plasma ball. That might be happening. But also what's happening is your AC will probably come on at a certain point, or your heat will come on at a certain point. Are you 100% sure that the thermostat where you're spending your time right now is set to save energy because you're not there? Probably not. It turns out that this is pretty universally true. So even just having a thermostat that did a setback not even that bad when you're not there of like 5 degrees makes a huge difference. Why aren't we doing that yet? What happens when you're not at work? This is the lovely brutalist building where ARPA-E has their offices on the top floor. Not complaining, it's a gorgeous view. So what happens in this room, for example? It's kept to a temperature that makes us comfortable, but there's also a lot of ventilation in here because humans and buildings exude a lot of volatile organic compounds and CO2. We need to keep the humidity level low enough so that we don't get mold, but we need to keep that CO2 down because that is really bad for us. What happens when we all leave here in an hour and a half? Is the ventilation going to be turned down? No, it's not. That ventilation is set for there to be like 250 people in here all the time. It takes more energy running those ventilation fans than it does to heat or cool these buildings. Moving big things takes a lot of energy. Spinning big fans takes a lot of energy. And we, with all of our phones and sensors in the world, we are so stupid when it comes to actually adjusting these things in buildings. So how can we save some of this energy? Well, let's go back to Holland, to this amazing man that was born in the 1500s. He is a really fun guy to read about. He was a complete Renaissance man. He did all sorts of amazing engineering feats. And he came up with a way to have thermostats do autonomous control with an oven to be an egg incubator. He did this by using a tube that looks sort of like an L. He filled it with alcohol, put mercury on top, and had a metal bar on top of that. When the temperature got too high, the alcohol would expand, it would flip the damper closed, and then the heat would go down. That was in freaking 1620, okay? Then there were many people who did this, but Andrew Erb said, okay, well, if I take two metals that have different coefficients of thermal expansion, I can make it such that they will turn a switch when the temperature gets to a certain level. So there's another way of using materials to do control autonomously without humans having to have a part of it to keep temperature constant. This is like works without electricity. And then we have my house last year that has a thermostat that is based on bimetallic materials and a mercury switch. Most people still have thermostats that are like this. It's a lot of mercury too. You can't just throw them away. So our technology has not advanced the way that technology has advanced in other areas for things like thermostats. Thermostats might sound boring, but when you look at how much energy we're wasting, it's totally not boring. And this is a quote that I love, and it might put you to sleep a little bit, but it's a really good quote, okay? Few housekeepers are philosophers enough to be willing to undertake the management of a machine requiring special mental effort where the advantages are not directly visible to the senses. What does that mean? It means we have no clue how much ventilation is being dumped into this room right now, and we have no clue that it's still going on when we leave because it's invisible. It means that people leave their thermostats set to room temperature in the middle of the winter because they don't even think to turn it down when they leave. When humans have to put mental effort into a decision, it will probably not work. How can we use technology such that humans don't have to think about this? Well, people have put together electronic thermostats, okay? We even have Wi-Fi controlled thermostats. We even have thermostats that have attempted to use sensors at the point of the thermostat to try to do this control for us. And to be honest, they really don't work. And there's a few really good studies out there that show why. First of all, anything you have to interact with is not going to work. And start to look at the thermostats around you, and you look at different apartments and homes and things like that. They tend to have really intricate user interfaces. So there's Alan Meyer at University of California at Berkeley has studied how complex these interfaces are and how much time does it take somebody to set a clock on a thermostat. I had a house in Midland, Michigan. At the time I was married, we both have PhDs in material science. That stupid thermostat was almost never doing the right thing. It was a pain in the butt, and we just left it really cold all the time. It was ridiculous. I mean, if two PhDs, in electronic materials can't be bothered to set their thermostat the right way, how is anybody else supposed to do it? It really was frustrating. And these have been getting almost worse and not better. The Wi-Fi ones are great, as long as you remember to go to your app on your phone. You have a nicer user interface, but you still have to remember to change it. Maybe you're excited about it and you do it for a few weeks. You're going to do this every day when you leave the house. You can schedule it and that helps, but it turns out that people just don't do that well. And there have been a number of studies out that show that not only do these not save any energy, in some cases people used more energy because they thought, oh, I have a scheduling thermostat, I'm being awesome, I can now crank the AC when I'm home because I'm saving so much energy. It's stunning how poorly these things work and how intricate it is how humans work with interfaces and why that works so poorly. So with all the technology we have, can't we solve this problem? And it turns out this is a really difficult problem to solve. So again, for a house, you're just trying to set a thermostat. For a building, you need to set the thermostat and these fan speeds. There's another thing that you need to do. If you're going to be playing around with fan speeds and ventilation, you need a way to measure CO2. Right now, you can buy CO2 sensors and install them in a wall. It's several $100s. They drift really badly over time, so they need to be manually recalibrated every year with a bag and gas and stuff like that. And you can just tell that the drift is a real problem. So they're expensive, but you can do it, technically. What you can't do is have a $10 sensor on a little button that you can stick on the wall and look at whenever you want, or on your phone or something like that. We talked with a lot of people, including real estate developers, which is really fun people to talk to if you've never talked to people in that field. And they all said, we want double ventilation. The last thing we want to do is reduce the amount of fresh air we're bringing into buildings. So this is a real issue, something we need to think about. And I keep hammering on this, but really, most buildings in the US are set up to do variable air volume ventilation and spin the fans down to whatever they need to be, but there's no data for them to use to be able to do it. So they just leave them on max all the time. IAQ is indoor air quality, and this turns out to be a really big market driver. People really care about the air quality in buildings to the point where that might be the thing that propels this type of a program into the marketplace. And why? Well, people have been doing studies looking at how CO2 levels affect human cognition. Normally, you want to keep the CO2 below 1,500. There's different standards for different buildings. And what a number of groups have found, especially this one group at UTRC and Harvard, is that people experienced definite, measurable changes in human cognition at levels far below what anybody thought before. This is really important in universities, for example. You ever been in a really packed lecture hall and you just feel like garbage? You get a headache, you get tired, you just feel crappy. Well, if you had a CO2 sensor on the wall and it said 3,000, that's why you feel crappy. But we don't have these sensors everywhere yet. This is a real problem. So even at ARPA-E, we have a really packed conference room sometimes, and we have CO2 sensors. I just went over, just wrote down the number, every 20 minutes. And at the end of the meeting, I'm like, anybody have a headache? And people are sort of like, nah. I'm like, yeah, that reads 2,500. And everybody was like, oh my God, really? So this is actually a significant issue. We need to know what this number is. And that will help indicate whether or not the ventilation is enough or not. And we have standards that tell us what ventilation should be, et cetera, but we really need the data. So how do we fix this? There's this key gap, which is that we need to know if there are people in a space, and we need to know how many people are in a certain space. So if we're talking residential, if we're talking your house, you just care whether or not there's a human home. You don't care how many there are. In a space like this, we want to know right now how many people are in this room. How would you do that? How would you do that with technology that is cheap enough that it pays for itself in 1 year? That is a very difficult thing to do. People are essentially hot bags of water. So you have hot bags of water moving around a space. So think about ways technically that you can measure that. And you can measure that and count the number of people that you have in a way that's really cheap that the market would accept. So there's this opportunity for these occupancy sensors, people counters, and CO2 detectors, where if you put them all together, you can now enable a building to use 30% less energy easily, likely much more. And they need to be very easy to install, et cetera, et cetera, et cetera. People have done studies looking at simulations showing that you could save up to 60% of the energy used in HVAC systems if you had occupancy data to feed into existing control systems. So what does this look like? What are we talking about when we think about sensors? I mean, pick up your phone. There's a bunch of sensors in that phone. Things like sensing temperature, super easy to do, okay? Again, sensing a person, it's a little bit more difficult to do. But we have these amazing low-power electronics platforms now. Does anybody here know what I don't know if you have these in your countries, an Amazon dash button? Who knows what that is? Okay, like one person, two people, all right. An Amazon dash button, I wish I brought mine with me. I have one that I use just for talks like this. It's a button, maybe it says like Tide on it or something, and you push the button and it orders Tide, and then it shows up from Amazon in a couple of days. And they have like hundreds of these. So if you want to order like soda, you push the soda button and then the soda comes. Everybody thought actually that this was an April Fool's joke a few years ago when they put this out. It seems like completely stupid, but it's not stupid. People love them. They're super cheap to make. And think about it's this tiny little thing. It used to have a AAA battery in it. Now they use a little sealed battery. And it has a wireless radio. It has a battery. It has a sensor, which is whether or not you push that button. People took them and started hacking them and used them to turn on their lights and to open their garage doors and stuff like that. Amazon actually put out a developer's kit version of the dash button so that you can go and program it to do a whole bunch of things, which I thought was super cool. I have one, and I haven't started using it yet. But this is a really good example of the fact that these really low-power electronics platforms already exist. What's missing is the actual sensor that you want to use. So if you want to just plaster this room with $5 temperature sensors, you can already do that today. But that's not going to tell you how many people are in the room. So how can you use a package like that and develop a sensor that can measure whether or not there's people around? Okay? There's a lot of different ways you could do this. You could use technology that doesn't really exist yet. You could use a bunch of sensors that do exist and use really novel algorithm development to try to fill in the gaps where they don't work in a complementary way, such that you can now sense people. I have to be careful what I say here because we do have an open funding announcement on it. There's the dash button. If you haven't seen one, I forgot I had a picture right there. There's the Tide. Okay, I'm not advertising for Tide. It's just the picture that I took. But there's a lot of interesting things that you can do, and there are people that have published some work in this area. So they just don't have money to be able to go after those ideas. And some of the ones that are published, so I feel comfortable mentioning this, for example, looking at Wi-Fi signal attenuation. Water will really attenuate signals in the bands of a Wi-Fi modem, for example. So is that something you could use? There are people in disaster recovery that look at micro movements of people. So if you can sense a heartbeat, you can sense a person. So can you have a sensor that's that sensitive to vibration in something like this? Again, that's something that's published. So there's a lot of different technologies here, but they need to be funded, they need to be challenged, and they need to be able to be made to be cheap enough and to satisfy customer requirements to make an impact. So when we look at cost metrics, for example, we look at how much energy can be saved in different markets. We look at costs. This is the national average for the US. It's a little bit different here. And to say, all right, If you want a return on your investment over 1 year, this is how much it's going to cost per square foot. That's a relatively easy calculation. This is harder, which is who's going to buy it, who's going to install it, who's going to use it. In buildings, the person who's often in the building is not the owner of the building, at least when you're talking about a commercial building. So who's going to buy it and install it? That gets very tricky. If you're renting it, maybe you can say, look, I'm not going to renew my lease unless you put this technology in, or something like that. Or if you want to get, say, a platinum LEED building status or something, then you sort of have to use technology like this. So that gets a little bit tricky. There's also a lot of issues around privacy. So one, we were talking with some people at University of California that were trying to do camera-based occupancy sensors in one of the dorms, and the students smashed all the cameras within a week. And they said, you can't have anything that even remotely looks like a camera. People will destroy it. There's an expectation of privacy where you live, which is different than an expectation of privacy where you work. If you work in Europe, I don't know if that's true here, it is actually illegal to detect whether you are in your office or not. So you have to figure out how to do this without identifying people. You just want to know how many humans are in a specific HVAC zone. There are issues like wiretapping laws. If you're going to use audio signals, are you allowed to do that legally? So there's all sorts of things you have to think about for a technology to be able to be used in the real world. And so we tried to talk with as many people as possible to figure out all of these issues so that we could include them in the funding announcement to say, all right, get your technology to work. Here's the technology metrics you need to meet. By the way, you need to satisfy all this other stuff too. And then we put that together in a funding announcement. So some of the things we look at are installation. If you need something that needs to be installed in that ceiling, that blows your budget before you even make anything. You really need something to be able to be installed and not be wired and stuff like that. Well, that's going to change your technology path. If you have to use a battery or something like that, and you can't have something hardwired, you're going to go a totally different path. So this is what my program is. It's called Sensor, which is Saving Energy Nationwide in Structures with Occupancy Recognition. I did not come up with that acronym. Somebody in my team did. We actually have like an acronym naming contest whenever a program gets approved, and we send emails out to all the PDs and the fellows and stuff like that. We're very proud of our acronyms. We have a very strong acronym game at ARPA-E. There's a Department of Energy podcast that's actually, it's quite good. The guys who put it on are fantastic. And one of the podcast episodes is all about how they come up with acronyms. It's a super fun listen. One of my favorite program directors talks a lot on it, so that's on the DOE website. So again, we have a funding announcement that's open right now. We call it a FOA. And so that's more or less why I can't really talk anymore about it now. If you care to look at it, you can go on the ARPA-E Exchange website and look at this 74-page long document or more that has all the details on it. And putting that together takes a lot of time, so we're very proud of it. So that's, at this point, I'm not going to talk about this program anymore. So if anybody has any questions, technical or otherwise, on this section, this is probably a good point to ask them. Okay.
Could you use, notice the mobile phone signals as they came in and out, as a way of noticing the people?
Can you use your mobile phone signals as a way to count people? There are people who thought of that. One of the problems with that is it requires you to have a mobile phone that is on and powered and probably has your Bluetooth on. We consider that a beacon, like wearing a badge or wearing a pin or something like that. And one of our biggest restrictions is no beacons. This needs to work whether or not people have their phones, because it becomes a safety issue. If your count is off by enough, then your ventilation is not going to be high enough. If you're home and your thermostat isn't doing what you want it to do, you might give that 1 or 2 tries and then you are never using it again. So we actually have very strict technical metrics for how well it works, and relying on a beacon will not give you good enough performance. So we actually specifically exclude that. It's a good question.
What about heat released by the body?
So those exist. So there's something called PIR sensors. PIR sensors are movement sensors, and so that's using materials that are very sensitive to temperature, and you have them right next to each other, and if something goes by, you get a spike on one and a dip on the other. Movement sensors do not count you once you're sitting still. and they are very, very easy to fool. So we talk about that in the FOA and the fact that movement sensors are not the type of sensors you need for this task. Thinking. Up there, on the top. Yep.
Will the increase in automation reduce the ability to change it manually?
Well, that's a good question, and I think that gets into more of a issue of controls. If I personally was building a thermostat, I would absolutely put in a manual override because I know people hate not being able to control that. I know that in one of the Nest updates, I think they took away the ability to do easy manual override, and it really frustrated people. But that's not a question we really need to answer here. We're just trying to get the sensor technology to exist, and then the thermostat companies, they will decide how to actually implement the technology. But that's a good way of sort of thinking how humans use these interfaces. Yeah. So there's a group, for example, well, all right, I have to be careful what I say here. There have been some publications out looking into that. One of the issues, obviously, is cost and how much power they use.
Just wondering, would it be possible to use like a sign-in system, so like people sign in and out of the room, but rather than having like different codes, everyone has the same code, so you kind of can't track who is in and who is out?
So, I mean, technically, would that work? Yes. Would people be willing to do that? Absolutely not. That's the problem, because that's requiring a human to do something every time they go somewhere. I mean, I worked for a company where I had a badge, where I had to badge in and out of the building every single time I went in and out of the building. And they still didn't use that information to do anything with the HVAC systems. And in some places, they might not legally be able to do that. And then you're wearing a beacon now, which is a different thing. Good. So that's a very good question. One of the issues with motion sensors going in and out of a door is if you have two people close to each other, how do you discriminate now that you have two people going in instead of one? Or 5 people going in versus 1? Or if you have somebody coming in the door when somebody else is going out of the door, how does it count that? So I do think that there's people thinking in that area. But again, we have very stringent technical metrics, and there's very few faults allowed. And when you're looking at just motion sensors, it becomes very easy to fool them with circumstances that would occur normally.
Considering this is mostly being applied in work environments or environments like this, where most people are sitting down if not moving, with a combination of an emotion sensor which would detect you and then sensors in the actual seats themselves in like offices sort of stuff, would that be sufficient in the meantime until better technologies were developed?
So that's a really good question. And so what I would challenge that idea with is starting to look at issues of cost and issues of counting people that are not sitting, and if you still get the count that you expect. It's a difficult question because we have very different types of commercial buildings. We have open workspaces, we have closed workspaces. Everybody might have their office door shut, or everybody might be in cubicles. You might have a workplace, like a retail workplace, where everybody's standing all the time. So you have to think about technologies that will work in all of these different use cases. And it's very difficult. And you can think of things that would technically work, but they are orders of magnitude away from meeting our cost metrics, for example. So you really have to start limiting your ideas of technologies to things that can fit those other metrics, and that's where it gets really hard.
Not specifically about, more about ARPA-E.
Sure.
Would like international people who, like, say, have a small set of group in, say, England, would have some kind of idea and they could get funding or something, and they go to the US if they're
So there's a question about international involvement in ARPA-E, and basically if international groups can apply to get funding. There is a waiver where if a part, I don't think a principal investigator can be, but I think if there's a part of a team that's from an international institution, you can actually get a waiver saying that that expertise wasn't available elsewhere, so I know it can happen. But in terms of being the principal investigator, I don't think that that's possible. But what I would challenge everybody to do is to think about this ARPA-E model, and does it exist in your own country? And what would it look like if it did? Are there areas of government funding that cover this? Are there national labs that cover this? Are there industry folks, VCs type of people like that, that would do work like this? ARPA-E is not the only way to be able to do work like this.
What's like the main issue about like how exactly
So when you think about what that means in terms of what's happening in a room, so you're talking about people moving, or are you talking about the temperature in the room overall as it's going up? I mean, there's a couple different ways to think about that. Some people, and there's actually a very good paper out about this, can you use the CO2 level as a measure for occupancy in a space? And it turns out it's actually really hard to do that because there's so much sort of air movement and diffusion, and it's very hard to actually pinpoint the number of people by looking at the CO2 rise. And because of the time lag of the sensors we have now and the drift, it's actually sort of impossible to do that. People have thought of putting them in return ducts, for example, and looking at how much CO2 you see in an air return duct, and showed that it really wasn't possible to estimate occupancy by doing that. You could also have local areas that actually have quite high CO2 levels and other areas that don't, and you have to be careful that you're not creating something like that. Now, if you're asking about, well, okay, everybody's sitting down right now, but a lot of people are moving their head a little bit, moving their hand. Hopefully everybody is breathing. So can we sense that movement and then say how many people in the room because of that? That gets to be a very interesting question.
What if, like, on the door, we have, like, a sensor, like, when you step on it, it has to go 2 feet step on, that's one person. When you enter, and when you exit, that's one person.
So there is a company out there that actually makes a commercial product, which is floor tiles that have little switches or sensors in them. And they're used to measure in retail spaces and also in other types of sort of commercial trade shows and stuff like that, where people are walking, how much time they spend in front of a display, and where they go next. This information is very, very valuable to people that make things like retail displays and stuff like that. The technology is very expensive. Anything involving flooring is really expensive somehow. So that is an example of something that would, in theory, work. The problem is the cost. And it's not just a little bit, it's orders of magnitude cost. Okay, so we'll take a couple more.
So you have so many different circumstances. Do you look at, when creating this technology, one piece of technology that can adapt to the different circumstances, or lots of different ones, including as needed?
That is an excellent question. So the question is, do you look at one technology that could handle all these different use cases, or do you look at a number of technologies that you could deploy in different areas? And I would say it's sort of a combination of both of them. I mean, if you can have something that is easily deployable everywhere and works everywhere, that would be awesome. That might not be the case. So when we fund groups in this area, we'll probably fund between 10 and 14 groups. They'll all be working on different things. They'll all have different ideas. And so some of those technologies maybe would work better in a space like this, and some of the technologies might work better in a different kind of space. So at the end of the day, you may come up with many different options for how it works. But people have to show how they're going to meet our metrics, and we actually put in the FOA, you have to have 3 very different building types, and you have to prove that it's going to work in these 3 different building types. So we do try to have something that can actually be sort of universally used.
So how is the progression of machine learning affected the way in which you can program sensors remotely, and how can we see that improving in the future as far as training computers to identify things that are humans and not dogs or cats, or something like that?
So this is a question about machine learning. This is an excellent question. I can't talk very much about it. You're absolutely right. I think that there's a very big role. I think the real question is a lot of people throw around the term machine learning, and they don't know what they're talking about. So when you say machine learning, it means it needs to be learning by getting data and the proper answer to the question, or else it's not going to learn. So you can't just say ... machine learning ... profit. That doesn't work. But if you're talking about here's the algorithm that we're trying to build, here's how we're going to train the algorithm by setting up different circumstances in a lab and telling the algorithm when it's right or wrong with 100% certainty, and then you train and you build that algorithm. That's good, and I think that there's a lot of potential for that in this space.
Just with your count with the sensors, how accurate does your count of people need to be? Would it be alright to just have discrepancies between how many people you have and how many people you actually sense in?
So we spent a lot of time on this calculation, And what we came up with is, in the residential space, it is acceptable to have up to 2 faults a year. And that information comes from talking, for example, with vendors of thermostats and stuff like that. So that means that up to 2 times a year, you notice that the thermostat is set incorrectly. In terms of counting people, we have a plus or minus 10%, which is the level that you're allowed to have based on a lot of US building standards. So there's that sort of plus or minus number, and if you are outside that number, then that's considered a fault. And it's also a very small number of faults that you're allowed to have a year. So that's a little tricky because it's not like there was some universal law that told us what that number had to be. We had to talk to a whole bunch of people and think about the actual use cases and see, okay, here's what a potential customer would accept. Okay. All right, I'm going to do one more. I am sure that there are people thinking about using RFID technology. That's all I can say. So, good question. All right. You can certainly have time for more questions at the end, but I wanted to move on just a little bit to tell you a little bit about this program called Delta. What does Delta stand for again? Developing efficient local thermal amenities or something like that. So Delta is based on the same idea that we use too much energy to heat and cool our buildings. This is not talking about ventilation anymore. This is just talking about heating and cooling. If you can expand the set points of your thermostat by just a few degrees, you actually save quite a bit of energy. But people don't want to do that because people want to be comfortable. So how can you help a person be physically comfortable in an environment that is a bit hotter or a bit colder than what they're used to feeling? And so there are people that have looked at this and what this means for different climates. In the US, we have a lot of really different climates. We have cold and humid, we have hot and humid, we have cold and dry, we have hot and dry, all over the map. So you always have to consider these different climates when you're trying to think about technology that can work in them, when you're talking about heating and cooling, keeping people comfortable. So when you look at thermal loss, for example, through a wall, you only have to change that set point just a little bit, honestly, to get 15% energy savings. That's a big deal. It turns out that depending, I would say, on the climate you're used to, the country you live in, the types of buildings that you're in, we get comfortable in a relatively narrow range. We also, for example, we might need to wear formal business attire. If you're wearing a wool jacket, you're going to be really sensitive to that thermostat reading 4 degrees higher than it usually does. So there's a lot of different things that go behind this, but the goal is to be able to expand that temperature band so that people don't even notice and that people are still comfortable. So how are you going to do that? So think about thermal loss from a body, and actually I learned a lot when I took over this program because I never really understood how important that radiation component was. So for example, you could be standing, let's say in my office at ARPA-E has this huge single pane window. And in the winter, it is freezing, but the air temperature is still room temperature. It's freezing because of radiation loss in the window. Radiation, it makes you feel different. So if you can control the amount of radiation loss, for example, through clothing, and change that from what it is now, you might be able to make somebody feel comfortable when they would otherwise not be comfortable. So what does it mean to have IR transparent clothing that is not visibly transparent, for example? So you have to consider things like this in order to say, okay, what do we need to work on to try to help people be comfortable? So there's a portfolio that was built. It's a number of different projects in a number of different areas. There's quite a bit of wearable technology, as you might expect. And these are clothes that would either actively heat or cool you. They might be something that a human actuates, or they might be self-actuating. So thinking about sort of these smart fabrics. So that's sort of a fun area to think about. We also have some other types of cooling. For example, this extended range energy transfer, it's a little robot that has a phase change material air conditioner that can follow you around. So there's a couple different ways to think about this. Berkeley looks at a wireless office suite that has, for example, insoles that can heat up, things on the desk that can heat up, things like that. So there's this group at University of Maryland, for example, that is working on this phase change material system. It's actually very interesting. I should have put the picture up here. So I actually took them to the big maker fair that's in the US about a year ago, and I don't know if you know what Maker Faire is. It's super fun. Just like thousands of people and lots of just engineers and tinkerers and stuff like that, sort of the whole maker movement. And there was a bunch of R2-D2s there. And so they rolled this robot out, and then all the R2-D2s went around it. It was very cool. So this little R2-D2 can cool you off in your office for 8 hours by blowing cold air. And it does it because there's this phase change material, basically sort of a wax, that can either harden or liquefy. And by doing that, it either gives off heat or takes in heat. I don't know if you've ever seen those hand warmers that are sort of like super cooled liquid, and then when you crack the little disc inside and it freezes, it gets hot, sort of like that. So this is useful because it means you can have an air conditioner someplace where you don't have connection with an outside wall. It means you can just use it exactly where you want. There's actually a lot of engineering that goes around behind a nozzle and airflow to cover you in a plume so that you don't really feel it. You just are comfortable. So there's a lot of interesting sort of human-based engineering that goes into that. There's another group that has looked at ways of actually having, say, shoes with radiators in them that don't even have to actively be cooled, but if you have, say, water that pulls heat away from the foot and exchanges it just with room temperature air, you can make a significant difference in the amount of heat that body can give off. And so they do a lot of work also with Stanford looking at sort of human subjects and how much heat you can actually release by doing something like that. So that's, that's not work I ever thought I would be involved with when I was in physics, but it's actually utterly fascinating. There's a group at San Diego that is looking at things like trying to embed thermoelectrics in materials, also materials that will basically get thicker and thinner reactively depending on what the temperature is. So when the temperature goes down, the material gets thicker, so the loft increases, and so you get warmer. Again, there's this group at Berkeley. Again, these slides are not very detailed as to what they're actually doing because that's all proprietary work. It's all work that they're doing right now. But at least I can share a little bit of it with you so you get a general idea. So there's a lot of other groups in that program, too, that I could talk about. There's one in particular that I really like called Other Lab. So Other Lab is calling it a startup is not quite right. It's like a group of a bunch of different startups in San Francisco, and it was started by Saul Griffith, who actually went to the University of Sydney in mechanical engineering. He then went to the US. He has a MacArthur Genius Grant, and he is a super smart guy. They have a Delta project. They also have a project that I was talking about when I was showing you that Sankey diagram and how difficult it is to actually break that down to get an answer like, how much energy did it take to make that cheeseburger? Does it matter if I'm a vegetarian? Should I buy an electric car? You can think of many, many different questions, and trying to understand the energy impact of those questions is actually really detailed and complicated. He wants to figure out that problem, and he's working, funded by us, to do that. He has a lot of videos online. I recommend that you go check some of them out. They're really fascinating. And it's that type of work that helps drive folks like ARPA-E and others to actually attack the right problems and to really understand where that impact can be made. Because a lot of times we might guess at an answer, and it turns out it's totally wrong because we didn't consider all of the different impacts of something. So I hope that that's given you a bit of an idea about sort of how we think at ARPA-E. I would say doing a job like this, for me, works very well, and I'm very happy there because I'm a naturally incredibly judgmental person. And that does not work very well in some other... All right, the 3 judgmental people just clapped. That's fine. If you are working, I would say, if you are working at a, large chemical corporation that does not want to do high-risk research, being a very judgmental person might not really be useful there or fit in very well. And you have to really reel it back. You have to learn how to do that. It's super fun to be able to have a job where you're supposed to do that and sort of let that out and have that be a useful thing. Part of being that personality type means that I have learned over time that I have a very good bullshit detector. And if you have one of these, it is a very useful thing because it means that you can do work like this in a lot of different technical areas, even if you are not a subject matter expert in that area. So if you have that tendency, don't shy away from it. It can be a useful thing. But it can also make you a little bit annoying, so be very careful with it. I've learned that the hard way. And most of all, don't lose track of what's important. And I just have to close with this. This is the most important person to me. This is my daughter, Violet. You saw her baby picture yesterday. This is at the Women's March in DC, and it was a very exciting time. So don't forget to make time for stuff like this. Thank you very much.